do for that one. B13. So I think this is more of a conceptual one. I think that people had some difficulty and challenges with. So going through this, right, the question, talks about Lewis acids. We haven't touched on acids and bases in this class yet, but what Lewis acids are electron pair acceptors. So usually what they have is an empty orbital, right? So kind of, along the line of the vernacular that I was using in previous problems where I was talking about drawing Lewis structures. But usually they don't fill the octet rule, right? So, group 3, elements, column 3 ones, a lot of those don't meet the octet rule initially right on their own, or even when they, form bonds. And so those are really good Lewis acids, because then now something that has a lone pair can easily donate electrons into it, right? So something like NH3, right, where it has that lone pair there, right? Or water, or anything, right? Those all have lone pairs, and so those are really good, what we refer to as Lewis bases, because they're electron pair donors. Right, those can then form new bonds by donating into empty orbitals on the Lewis acids. And so in this case right here, right, we're talking about trimethyl aluminum and aluminum hydroxide. And so, right, we can draw out both of those structures in these cases. And so if we're looking at aluminum, trimethyl aluminum, right, so it's just simply aluminum in the middle, and then we have 3 methyl groups, right? So three CH3 groups off of it, right? So we have a carbon with all of these guys. Right there, right? And so going through, right, so each one of the carbons has a full octet, right? They all have 4 bonding pairs. The aluminum only has 6 electrons around it, right? So it doesn't have a full octet, but that's perfectly fine, right? Because it's a row 3 element, right? It's a group 3 element, and so it's not row, column 3, right? So it's a group 3 element, and so those don't have to follow the octet rules necessarily, right? And so that right there is perfectly fine in that case, right? And there's no formal charges or anything, so we don't have to worry about anything there. If we do aluminum hydroxide, right, we have aluminum, and so that's going to have 3 hydroxide molecules around it. So we have OH, right? And so each one of those oxygens has lone pairs. Right there, right? So all the oxygens have full octets as expected, right? The aluminum doesn't have to, right? It has 6 electrons around, right? It has 3 bonding pairs, so that's all good as well. Yeah, and so right, so that's, there's no formal charges, right? That's a pretty good description of the bonding in each one of those cases. Now, part B, right? It talks about aluminum, trimethyl aluminum being a stronger Lewis acid compared to the aluminum hydroxide, and we can use resonance structures, right, to make that argument, right? So to be a Lewis acid, right, you have to have an orbital that's completely empty. And so in the case of the trimethyl aluminum, right, there's no way for us to draw any resonance structures where you do start filling in that orbital, right? You start forming double bonds or triple bonds or anything, right? So, each one of those carbons has 4 bonding pairs around it, right? It doesn't have any lone pairs, so there's no way for you to draw a resonance structure for those to go in. Whereas in the case of the aluminum hydroxide, right, that's not true. Right, if we look at the aluminum hydroxide, what we can do is we can have, one of those lone pairs on that oxygen actually form, a double bond with the aluminum, right, and kind of donate itself into that empty orbital on the aluminum, so that, what you get then is this structure right here. Right, so that's you have that right there. And so going around the aluminum, right, it has 1, 2, 3, 4, 5, 6, 7, 8, right? It has a full octet now. And so what you can then do in this case is also count up the formal charges, right? So the aluminum now has a formal charge of -1, right? And then this oxygen right here is a formal charge of +1. So, right, so it's not really the most reasonable or stable resonance structure necessarily, but it's a valid one, right? Everything meets the octet rule. Everything, we didn't add in any electrons, we didn't take any electrons out. The overall charge of the molecule, is still the same as it was before, right? It's just that, we have a positive charge on an oxygen, which isn't the most favorable thing. But it's still valid, right? And then same thing, right? We can keep drawing resonance structures where we start donating more and more from the different oxygens, right? And so we have this one is the double bond. We have this one that's the double bond. Right? And so now, right, both of those oxygens, right? Both of them have positive charges, and now the aluminum has a 2- charge in this case, right? And so the aluminum now is going into the extended octet space, which is fine because third row element, so that's perfectly acceptable. And then, right, we can keep on going, and then now we have all double bonds, right? Because we can have this guy come into here. Right, and so then we have positive formal charges on all the oxygens, and then a 3- charge on that aluminum. Again, not necessarily the most stable of resin structures or the most believable, but still technically valid. And that shows, why, aluminum hydroxide is actually, a worse Lewis acid, because it's not a completely unfilled, orbital that's on the aluminum, right? You're actually getting some donation that happens between the lone pairs of the oxygen into that to kind of, reduce its ability to take in a brand new lone pair from a completely different molecule, right? So even though, right, all those resonance structures aren't completely valid, they're still important, still part of what we're looking at.